Hello, welcome to the course on Introduction to Computer System Design. So, in the last class, we have studied the digital transformation hierarchy. In particular, what are the different layers of the design aspects when we study this entire stack of problem solving on digital computers. So, if you remember, we started with how electrons are manipulated or orchestrated using microelectronic devices like transistors, diodes, and so on. And on top of that, we build electronic circuits, and how we are going to kind of take a deeper look into how this digital logic or logic is going to be combined with digital circuits to create to implement digital logic. And on top of that, we are going to see that how different logic circuits could be combined together in order to use it as a fully functional computer, which is often referred to as a microarchitecture of the underlying system. So, primarily, as discussed in the introductory class, our course contents are going to focus heavily on the logic part. So, this is where we are going to learn about the digital logic and how this digital logic is going to be used to implement logic circuits, right? And those logic circuits, as you may know, that is going to be implemented using some gates and so on. So once we know how this digital logic could be used to implement digital circuits, we are going to take a look at the microarchitecture of a CPU or a central processing unit or a computer for that matter. And it is going to consist of various such logic circuitaries, and that will be the focus of the second part or the next part of this particular course. So this is what we are primarily going to cover as a part of this introduction to computer systems design, and as a end goal, we are going to learn how to implement a very simple CPU using digital logic elements. So that is going to be the focus of the second part of the course. So this is just a recap from the previous lectures. Okay. So again, this is another image which is again borrowed from the previous lecture. Here, this is more of the transformation hierarchy in action. Here we could see that starting from a simple gate which could consist of a few transistors, and we went all the way to a very complicated computing system like a smartphone. And if you understand this, all this entire set of software, the applications, all the Android operating system, for example, is running on the smartphone, but eventually uh, everything is going on by orchestration of some gates underneath, right? So our goal is going to kind of demystify what lies under this complicated piece of hardware and look at various stages what kind of modules are there underneath and how are those modules formed, or how can we come up with a design of a module. We are going to know the principles or the recipes behind it, right? So please keep these two pictures in your mind, that even if it is a very complex system, however complex be it, we are going to disintegrate the system into simple modules. Although we have shown here various kinds of stages, like a PCB that is broken up into integrated circuits, that broken up into modules, and that broken up into cells and so on. But the main takeaway point is this: whenever we are trying to build or design a complicated computer system, you need to think more in terms of how can you break it or disintegrate it that into simpler components, and you should be having a ready-made recipe to have or to build those simpler components, right? So those are the, I would say, some kind of a Lego block, right? I like using this term because those are like the building elements in order to build something bigger. So if you think of the cell, for example, as a building block, this is a simpler low level component or your Lego block, which is going to be integrated. Like many such Lego blocks are going to be integrated in some ways in order to create circuits or in order to create modules that has much more richer functionality, right? But if you want to directly design a very complicated module, you might be overwhelmed or it might become very complicated, right? And so we are going to see how, what are these Lego blocks. There are some common Lego blocks, like for example adder, or you have a circuit which is going to, let's say, multiply two numbers, right? So this could be the basic definitions of cells, and we are going to use these cells to make something more complex. Okay, so just revising another aspect of this analog and digital things that we brought up again in the last lecture. We had enough motivation why we do not want to use the real continuous voltage values for representing data, and what is the motivation of using digitized values or discrete values or digital versions of these voltages, right? So we are going to use the voltage in a thresholded manner, right, digitally. So we are going to encode only one bit of information, and that one bit of information has two possibilities or two states. One is 0 and the other is 1, but you can come up with any names, right? So these are not really zeros and ones that we know of in our decimal system. It does not have to be the case. It basically has two states. It could be high, it could be low, it could be 0, 1, or anything else for that matter, right? So, and we use the same uniform representation across all the components in the digital system. This is very important, right? So whatever convention we create for this nomenclature, this has to be uniform across all the digital components in the system, right? Because otherwise there will be a state of confusion. If you say that anything more than 4.5 is 1 and anything less than 4.5 volts is 0, right? So let's say for anything, if your voltage is greater than 4.5, then we say this is 1. If anything is lesser than equal to 4.5, we say 0. Let's say this is one system. This is component 1. Whereas a component 2 could say that voltage is greater than 3.5 is 1, whereas voltage lesser than 3.5 is 0. So this is component 2. Now if both these components are in the same system, this is going to give rise to some amount of ambiguity, right? So because anything greater than 3.5, so if you have a value like the 3.9, which is interpreted on the component 2 as 1, whereas it is interpreted in component 1 as 0, right? So that's the reason we are trying to say that the same uniform representation across all the components in the digital system. So whatever be the component, they need to agree to the same set of values. And the way we had two ways to represent the voltage value in a digital form. The first one was thresholded. So this is exactly the same that I have shown as an example on the right hand side. So in this case, the thresholded voltage was 3.5 or 4.5. So anything which is more than the threshold voltage is going to be interpreted as 1, and anything which is less than the threshold voltage is going to be interpreted as 0. So this is how we are going to digitally represent that voltage in these two states. That is how we interpret that. And of course, this had an issue as we have discussed, because anything which is very closer to the boundary in between 0 and 1 could be contaminated by noise, and which is going to push this particular value to the to a different side, right, leading to a false interpretation. For example, if you have a value x, which is going to be really interpreted as 0, because the voltage, let's say this is 0, this is the maximum voltage is 5 volts, and the thresholded voltage could be taken just like 2.5 volts, right? So if you have a value x or a voltage which is, let's say, 2.47 volts, this is going to be interpreted as 0, right? But as you see that these are real systems, and there would be always some kind of a natural noise that will be present in such information that could be contaminated with this kind of information. So x could easily be contaminated with noise, and that noise could push the value of x to the right hand side of this boundary, right? So you can end up with the value of x being, let's say, 2.52 volts, right? Which means that it is going to be interpreted as 1. Okay, so this is the reason we typically do not keep this convention, or we do not keep this methodology to interpret zeros and ones. Rather than that, we define a band. Okay, so what does this band do? This band is supposed to define a forbidden zone, right? So you cannot have any values in between this lower value of the voltage threshold, which is indicated as VL, and the higher value of the voltage threshold indicated as VH. Okay, so if you have now any value x which is lower than VL, it is going to be interpreted as 0. If you have any value which is more than VH, it is going to be interpreted as 1. Okay, so if there is any accidentally contaminated value, right? So if you have x which is going to be contaminated by noise, which either becomes more than VL or less than VH, those values are going to be ignored because those are considered illegal by the system, right? So probably you need to reread the value, or kind of recalibrate the value, or correct the value, and so on, right? So there is no direct chance of interpreting a 0 as a 1 or 1 as a 0, right? So that was the minor issue with the previous design. So we had to come up with this band based design where anything in between VL and VH are going to be interpreted as illegal values. So that was about the representation of the voltages digitally, and you can have as many states as you feel like. In this case, we have shown 2 states because we wanted to express only one bit of information, but you can also have multiple such threshold levels, and that can be used to determine multiple such states, right? So even if you want to have, let's say, 3 states, then you should define 3 such decision zones, right? So you can have interpreted 0, then there's a forbidden zone, then interpreted as 1, then there is a zone, and then there is an interpret as 2. So you can have 0, 1, 2. Given the voltage value, you can have either one of these 3 possible outcomes, right? So we stick to the binary digital system in this digital circuits, particularly because of the ease of the implementation, the efficiency of the circuits. It is cheaper, smaller, right? So the design, the actual design becomes efficient, right? So that is the reason we choose not 3, not 5, not 4, but we choose only 2 states, right, for a given bit. Okay, so digital means finite number of values. Don't think that digital always here means just zeros and ones. It's a binary digital system that is with a base of 2, and that is the reason we are going to have 2 states or values. Okay, so in this case here I have shown another example where the VH is equal to 2.5. So anything which is greater than VH, that is this zone, is going to be treated as 1, and VL is going to be 0.5 volts. So anything which is less than VL is going to be treated as a 0. So this is about the binary digital system. So I think there is a brief recapitulation from the last class, or the last set of classes, where we looked at how to take a complex system, break down into easily manageable parts that are going to be implemented using some logic circuitry, gates, and so on. Then we looked into the fact that why do you need to use digital system, not why not use analog voltage values to represent information. What's the issue with that? We looked at some examples, or more of a not from a theoretical point of view, but using some empirical evidences. We just tried to convince that why using analog voltage values for representing information could be a problem, and why do you use digital system, in particular a binary digital system, to represent binary info or to represent information digitally. Okay, so this takes us to the next part, or we are going to continue with some of the prerequisites like Boolean algebra and so on that is going to come up, right? But this is just a prelude to tell you more about the digital logic design. So I'll just elaborate on the fact a little bit. So currently we did understand the meaning of the word digital, right? So we understood what do we mean by a digital value or a digital way of representing information. Okay, so next what we want to do is that we want to create circuitry, or we want to, at the end of the day, we want to create computers who is going to manipulate or compute on such digital data. If you remember from the schematic of von Neumann, that what I showed in the very fast lecture was that we had a compute unit, we had a communication unit, and we had a storage unit, right? So when we say we are trying to create such designs or digital logic design, we mean that we are going to create circuitry which is going to, let's say, work on some kind of data manipulation of the digital information being stored in the storage units, right? So I gave an example of adding two numbers. Let's say you have a one number, you have b, and you want to create a circuit which takes a and b and output c, where c is equal to a plus b, right? So this is the logic that we want to design here. So when we say logic, right, this typically refers to the hardware logic. So you are essentially going to design a system or a hardware which is going to consume these two inputs a and b. Note that a and b are represented as digital information which is stored digitally in the storage units. For example, let's say a and b are actually stored there. So it is going to fetch those, maybe using the communication unit, and the logic part is going to take a and b and see how a and b, how the individual bits of a and b can be manipulated, or some kind of action needs to be taken on those two digitally represented information to compute c, which is nothing but the sum of a and b. And again, maybe c could be stored back to the storage unit. So this is what we mean by the designing of the logic, right? That's why we call it digital logic, because it is going to act upon digital information. Okay, so we need one more thing to do this, which is indicated on the left hand side. So that is Boolean algebra, right? So digital logic typically is more abstract, which is based on manipulation of logical elements. For example, two logical states we were talking about was, let's say, true or false, or high and low, up or down, 0 or 1, right? So these are Boolean variables or Boolean values, right? They can take either two kinds of states, and the entire set of algebra, or the algebra for manipulation of these logical variables is called Boolean algebra, and that is what gives rise to the digital logic, right? And so this was invented or shown that you can actually do maths using this logic, which is typically called the Boolean algebra, which was introduced in 1854 by George Boole. And this is basically the mathematics of these binary values. Okay, So all these values are going to take these two states. Okay, and that was way back in the 1800s, so 1854. And after that, what happened is, this is a picture of Claude Shannon, who took this concept of this digital logic or Boolean algebra and tried to apply that in actual digital circuits, right? So which gave rise to this new field of digital electronics in the early 1930s or like early 1940s, right? So what was done is, despite the existence of, in those days, relays and vacuum tubes, digital electronics did not emerge for more than 30 years. So everybody knew about the existence of Boolean algebra. There was this existence of relays and vacuum tubes, which is basically some proxy of the transistors, because transistors was not invented at that time. So, but this could be thought of as an analog of these transistors, because they could also be used almost like gates, right? They could have, they could amplify the signal, they could kind of create a gate for passing the current or not passing the current, and so on. So this could have been invented, but it was Claude Shannon from Bell Labs who later came to Bell Labs, right? So he noticed the similarities between Boolean algebra and electronic telephone switches, right? At that time, most of the circuits that was being developed went to telephone line switching. Okay, maybe in a networking class you will know more about them, but you can, for now, you can just assume that he is the one who married these two fields. They took digital circuits and as well as Boolean algebra, and then tried to see that how can I formalize the formation or creation of a, or design of a digital circuit using the Boolean algebra principles. So what we need to understand is some prerequisite for creating digital circuits, as you can understand, is to understand the underlying principles of Boolean algebra, or the underlying theorems and the axioms that exist, right? That will help us to come up with a methodical way to create such circuits. Okay, so the typical problem will be this: it will be given some kind of a problem and will be asked to create a circuit for that. And for understanding that, you need to understand how the, what are the inputs first of all, and how are those inputs acted upon. So the circuit that you are going to design is going to act upon those inputs and create an output, right? And those inputs are typically digital data, which comes under the umbrella of binary values or manipulation of binary values. And you can apply Boolean algebra to that problem, and for making your life simple. Okay, so just reiterating the lesson plan, because from now on we are going to go full force into understanding the various design principles that would be useful for us to create a computer or a processing unit, or understanding the basic building blocks of the computer organization, right? So in module 1 we did cover the foundations to some extent, and introduction to the digital world, right? And now we are going to cover some grounds on Boolean algebra and what are logic gates. So once we know this, and to some extent we know what is the problem of designing logical elements. So we are going to design logical elements. There are two categories, sequential and combinational. So we are going to go into those directions, but before that we have to equip ourselves with the prerequisites or the knowledge about Boolean algebra. So typically some axioms that you need to remember, or some of the theorems that you need to remember, that will be useful for designing efficient circuits, right? So you have to take this as a prerequisite targeted towards better design of circuits. Okay.